Good morning, everybody. We are going to continue with exponentials and we're going to talk about something so important today. It's called growth and decay, okay? And as similar as growth and decay are, they're also very different. So, before we even get to the do now, because I just want to explain something to you first before we hit the do now, I'm going to define growth and decay and show you how you know you're looking at growth versus decay. So look at these growth and decay equations. This one's growth, this one's decay. And if you notice, there's only one teeny tiny difference between the growth and the decay equation. Growth has a plus in the middle. Decay has a minus in the middle. Y equals a 1 plus r to the x. And decay is a y equals a 1 minus r to the x. So what are all these variables? Okay, well, your A value is your initial amount before you're measuring your growth or decay. So it's what you're starting with, okay? A is your initial amount. Very important, your R value is called the rate. And they usually give it to you as a percent. But you need to put a little star right here. This is really important. You must turn into decimal. Okay, the R value is going to be a decimal value that you put in. And your X value is going to be your time. It's how many years have passed. For you guys, it's mostly going to be just annually years. So how are you going to know you're looking at growth versus decay? Well, if you look at your equations, and we've talked about this already, your growth is increasing, right? You could see this graph from left to right going up. This is growth. And when you're staring at the equation, most important thing I could say to you, how do you know your graph is growing? Look at your base. When your B value or your base right there is greater than 1. So as long as your base is greater than 1, the graph is growing. It's considered growth. Now, on the flip side, look at your base here, 0.5. Look at this graph. It's going down, or what we call decaying. Okay, so not just when it's less than 1, when your base is in between 0 and 1, that is when your graph is going to be decaying. Okay, so when you come back up here, I want you to now look at the bases. Okay, so what's a base? Remember, how are you going to figure this out? Look at the base. Okay, so if the base is greater than 1, it's growth. If the base is in between 0 and 1, it's decay. So now I think even more important is, what numbers represent the base? The base is the number that is being raised to a power. So understand, this is the base. This is the base. Base, 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 base. In number 4 and in number 3 and 6, the 2 is not the base. In number 5, the 4 is not the base. It's what's being raised to the power. Okay, so look at the first one, 0.5 to the x. So here's your question. Is 0.5 greater than 1 or in between 0 and 1? It's in between 0 and 1, so number 1 is decay. Okay, how about 1.5? That's greater than 1. This is growth. You could also check by putting it in the calculator and seeing what the graph is doing. Number 3, here's your base of 3. That's growth, greater than 1. Number 4, your base is 4. It's growth. Number 5, your base is 2/5. That's less than 1 because 5/5 equals 1. So if it's less than 1, it's decay. And here, 4/3, a little tricky. Remember, 3/3 is 1. So this is 1 and 1/3. That's technically 1 and 1/3, which is growth. It's greater than 1. Okay? So I want you at least to be able to know when you're looking at growth versus decay. Okay, so let's try an example. We're going to go to Funtown. Okay, and in Funtown, it tells us which of these following equations can be used to determine the number of people living in Funtown, New York. Okay, so when you're looking at these equations, I want you to just take note of, technically, these are your x values, these are your y values. So your x values are going up by 1, 0, 1, 2, 3, 4. So you're technically looking at what's happening to the y values. How are they increasing? Right? From 1 to 3, 3 to 9, 9 to 27. Hopefully you see you are multiplying by 3. Okay? Means there's a constant ratio of 3. So could this ever be linear? Can't be linear. So here's one thing you could do. Let's just say you're not really knowing, oh, is it exponential? Is it linear? Is it quadratic? Put them in the calculator. So like just for instance, number 1, it's 3 to the power of t. Okay, we don't know a power of t, so we're just going to use the power of x. So let's say, hold on, I want to do this. I want this. If I go 3 to the x, and I go to my table of values, okay, and that one went from 0 to, what, I think like 4. Table went from 0 to 4. So if I go 0 to 4, and I look at my table, 1, 3, 9, 27, 81. Jackpot. Exponential. That's my answer. Now I'll just prove to you that another one wouldn't work. If I just try, let's just say number 2, 3t squared. So here I'm going to go back here and just do 3x squared. It's a parabola, but more important, I need a table of values. This table goes 0, 3, 12, 27, 48. Not what we're looking for. So this one is linear. Highest exponent is 1. This one is quadratic. Highest exponent is 2. This one is exponential, but it just won't have the same table. If I do 3 times 3 to the x, so if I just clear these out and I do 3 times 3, and I raise that to the x, so that's also exponential. But if I use my table and I go 0 to 4, my first value, 0, is 3. 1 is 9. That's not what we have. 0 is 1. 1 is 3. So this one just had the wrong table. I would just write wrong table. It had to be choice 1. Okay, so let's try another one. Let's look at number 2. According to the U.S. Census Bureau, there was approximately 7 million households with access to computers in 1984. Okay, so I'm just going to highlight 7 million. Okay, the computer usage in the United States, keyword, grew at a rate of 14% per year. Okay, so which of the following could be used? So if we're hearing that word grew, we know it's got to be growth. So what's our growth formula? Y equals A, 1 plus R to the X. Okay, so here instead of Y, they're using this N of T. Okay, the number of people using these computers in 1984. So what is your A value? Your A value is your initial value. What's your initial value? Your 7 million households, and they just write it as 7. Now I'm going to do 1 plus, what's the rate? 14%. Here's the hard part. 14%. You never plug it in as a 14. You plug it in as a 0.14. Why? It's this move 2 to the left. So I am going to plug in 0.14, and I'm raising it here. Instead of using an x, they're using t for time, especially because you have t here. So now you don't see that question. You don't see that answer, 7 times 1 plus 0.14 to the t. But is there anything you could do to that question to simplify it? Yeah, you could simplify inside those parentheses. N of t equals 7 times 1.14 to the t. 1 plus 0.14 is 1.14. And there's your answer, choice 3. As easy as that. These are going to be very easy. You're going to see exactly what you want to do. Okay? So let's take another one. Look at number 3. Let's say you have $750 to invest in a savings account and it earns 5% interest compounded annually. Write a function, really important word. This keyword function, I want you to take note. It means you need an equation, okay? Function that will determine how much money you will have after T years. Okay, so let's do that first. They first want a function. So I'm going to name my function anything. F of t, V of t. I'm going to say V of t, which is the value, let's just say the value of this money over time. Okay, so is this growth or decay? If you're putting money in and it's earning interest, it's got to be growth. So we're going to use that same equation. Y equals A 1 plus R to the T. Well, what's my A value? What am I initially investing? $750 times 1 plus. Okay, what's the rate? The rate is 5%, but we never plug in a 5. We move that decimal 2 to the left and it becomes 0.05. And I'm going to raise that to the t. So remember, you go boop, boop, 2 to the left becomes 0.05. Now, this is the first part. This is A, writing the function. A, write the function. Now, part B, I'm making part B. How much money will you have in the account after 20 years? Okay, so what is represented by 20 years? T, time. 20 years is time. So all that means is if I plug 20 in for time, I do 750. I can make this 1.05. I don't have to. You could keep it as 1.01 plus 0.05. And I'm going to raise it to the 20th power. So I'm going to go into GeoGebra. And I'm going to clear this out. And I'm going to type no equation. I'm just going to type the 750 times. You could do 1 plus 0.05 or 1.05. And I'm going to raise that to the 20th power. Hit and enter. That's your number. Now, they didn't tell you exactly what to round to. So if it's money, you're going to round to the nearest cent. So the value after 20 years is $1,989.97. It's 973. That 3 tells you to keep it a 7. Okay, so that was part B. All right, let's try another one. In the 2000-2001 school year, the average cost for an annual 4-year private college was $16,332, which was an increase of 5.2% from the previous year. If this trend were to continue, so now look at the equation. This is so nice. They give you the equation. So notice the equation. It's a growth equation. How do you know it's a growth equation? Look at your base. Your base is greater than 1. This is growth. Okay? And you have your initial amount, 16,332. Now, where did 1.052 come from? We took the 5.2% and we converted it 2 to the left, 0.052. Any percent between 1 and 9 is going to have like a 0.01, 0.09, 0.05. So here's 0.052. So now all they want you to do is find how much it would be worth after 4 years, C of 4. So C of 4 would look like this. 16,332 times 1.052 to the 4th power. Okay, so again, I'm going to go back into my GeoGebra. There's going to be a lot of GeoGebra. And you're going to do 16,332, parenthesis, 1.052, and raise it to the 4th. Okay, and there's your number. Remember, you're going to round it to the nearest Does it say? No. So if it doesn't say money, you're going to do to the nearest cent. So looks like $20,003.33. Okay. Now it says, if this trend continues, how much would parents expect to pay for their newborn baby's first year of college, assuming that their kid will enter college in 18 years? Okay, same concept. Instead of doing after 4 years, we need after 18 years. So take your 16,332 times 1.052, but now instead of raising it to the fourth, we're going to raise it to the 18th power. So again, we're going to take GeoGebra, take our 16,332, notice no comma, times 1.052, I missed a 0.052, and raise it to the 18th power. So how much? 40,000. So this is $40,674. Looks like and 54 cents because there's a 3 after the 4. So 54 cents. Okay. The next one, it's talking about depreciation. And I feel like we've spoken about depreciation. It's a really important concept, very real life. But as cars get older, they're worth less, okay? And this is called depreciation. As they get older, they are worth less. Assuming you bought a car in 2007 for $13,700 and it depreciates at 20% per year. So let's just talk about depreciation. This is a really important word. Depreciation is another word for decay, okay? So this is a decay question, which means you got to be thinking about y equals a, 1 now minus the rate to the t, okay? So it says an equation that will be modeled by this. V of t equals 13,700 times 0.8 to the t. So I want you to take note of this base, 0.8. Does anybody know where 0.8 came from? You know what 0.8 represents? 80%. And I want you to think about, if you got 20% wrong, you were taking off 20% of your test, what would you get? You would get an 80. So think about it. If you had $13,700 and this formula tells you to depreciate by 20%, remember 20% is 0.20 because you're moving 1, 2 to the left, 0.20 to the t. So technically, I'll make it V of t. Can you simplify 1 minus 0.2? Yeah, it's 0.8. And just know that's exactly what they gave you. I want you to know where 80% or 0.8 came from. It's the 1 minus the rate. So they want to know, how much is your car going to be worth? V of 1. That means after 1 year. So all you need to do is take your 13,700 times 0.8 and raise it to the first power. So I'm going to bring this up. I'll clear everything out. It's getting to be too much. And I'm going to do 13,700 times 0.8. And I'm going to raise it to the first. That's not what I meant to do. Technically, I don't even have to raise it to the first. There's my number. Now, hold on. That's not my number. I multiplied it by 0.8. It's 0.8. So 13,700 times 0.8. Again, do I have to raise anything to the first? No, but there's my same number. So the value after 1 year is $10,960. Now let's just talk about why that makes sense. Is your car going to be worth more or less? They told us less. So when you're doing decay, it's going to be worth less. When you're doing growth, it should be more than what you started with. 6, 7, 8, 9, 10. Okay, I think I'm going to give you guys the rest on your own. Okay, so notice, you're talking about in the next example that it dropped by 1.1% per year, okay? And it was originally 300,000. So I want you to immediately think to yourself, it dropped. It has to be a decay, which means you need a y equals a 1 minus r to the t. You could use y equals, you could use f of t, v of t, whatever you want to use. But let me just say one other most important thing. Here's what kids are going to do. They're going to write, okay, v of t equals 390,000 times 1 minus, and then for the r, they're going to want to put in 1.1. You can't forget 1.1 is a percent. You must convert that into a decimal. I know it's a decimal there, but when you convert percent to decimal, you move 2 places left. So if you move this 2 places left, it'll be 0.011. That's the number that goes in here, 0.011. And you could raise that to the t. If you use v of t, then you make your exponent t. If you're just using y equals, you can make your exponent x, whatever you want. Okay, so the next part, just be careful. They're asking it around to the nearest dollar. They want it after 5 years. So I'm going to let you guys try the rest. I will post an answer key, but please try to do it on your own and see how it goes. Okay.